Hopefully you have been able to see the previous recordings. If you've missed any of the sessions, this one is being recorded as well. I have put up the week 8 work. We've got some longish videos this week, so there's a slightly longer format because I think that's the way that the derivations worked. You've hopefully got used to that by now. And just to point out that one of the examples in worksheet 4, question 2, so this is for the weekly work, the radiative lifetime of the electron. I've just made a stupid error and someone's pointed it out. So what I'll do is I'll rewrite the answer to that one and I'll put it into the notes as well at some point. It's not a major thing right now. You should be looking at cyclotron radiation, which we'll be covering in the next section. You should be looking at that in detail, but I'll come back to that in the next week's work. All right, so as usual, please ask questions in the chat. And this week we're going through the week 8 problems to augment what we did on coaxial cables and cavities. So remember that we are moving towards the idea of guided radiation, and in the coaxial cable, we previously drew the electric and magnetic fields that occurred in the coaxial cable at a given moment. So that's what I'm showing in the worked answers, which are available on the Blackboard site. So as we see here, so we imagine here, this is a DC situation. So in our DC situation, I am drawing a central conductor, which is carrying a current I in one direction. And we can consider that the ground, the earth, is carrying a current in the opposite direction. But we also think about the voltages which are being generated on the central conductor compared to the earth that surrounds it. And if the central conductor is positive, we have a radially outward pointing electric field, and that the electric current, which is flowing along the wire towards the right, gives rise to a magnetic field, which is circuitous and which goes clockwise when viewed along the direction of the wire. And we can see here that the electric field is radially pointing outwards, whereas the magnetic field has this so-called toroidal orientation. And if we look close up at these two fields, we can see by inspection that the electric field and the magnetic field are perpendicular to each other everywhere within this dielectric material, which lies between the core and the grounded sheath that lies around the outside. And just to remind us, the electric field outside this coaxial cable is 0, and we can obtain that because, of course, we know Gauss's law. And similarly, the magnetic field outside the grounded sheath is also 0. Now, the electric current, the current is flowing along the central conductor, and that defines our Z direction. And of course, that is perpendicular to the electric and the magnetic field, again, everywhere within the dielectric material. Now, the interesting question here is where is the power being carried in this situation? So let's look at 2 situations. So I'm going to look at 2 particular times. And the first time I'm looking, I'm thinking, I'm now going to take a cross section through the cable, and I'm going to look. So I look on the left-hand side firstly. So on the left-hand side, I'm taking a cross section through the cable. I'm imagining still a DC situation, which means there's a constant current flowing at all points along the wire. And I imagine that there is also a positive voltage, which is also the same all the way along the wire into the page. So I have exactly what I had before. I have the electric field pointing radially outwards, and I have a constant current flowing. So the magnetic field is pointing toroidally at right angles as it makes circuits around the cable. And again, as we said before, the electric and the magnetic fields are perpendicular. And if I take the cross product of the electric and magnetic fields, the direction it points of our pointing vector points in the same direction as the current. So we can see here that on the left-hand side, the DC power flows parallel to that current. This is for a DC situation of a current flowing always in one direction, and the power also flows in the same direction. And we can see, can't we, that the Poynting vector arises because of the magnetic and electric fields in the dielectric, not in the conductors, but in the dielectric that lies between the conductors. And the total amount of power that flows along this cable is the integral of this Poynting vector value, the S value, over the area of the dielectric, not the area of any of the conductors. Now let's look at a situation on the right, which is the situation for AC. So really the two pictures, the left-hand picture and the right-hand picture, apply in this situation where I have an AC current, where the left-hand side is the moment in time at some particular value of Z when I have a positive voltage being generated on the central conductor compared to the ground. On the right-hand side, we are 180 degrees different. The voltage on the central conductor at this particular value of Z has inverted. It's now minus. So now the electric field points towards the conductor at this particular value of Z rather than pointing outwards. And of course, at this point in time, the current is also flowing in the opposite direction. So rather than flowing into the page, the current is actually flowing out of the page. So we remark, don't we, that the current which is passing into one end of the wire is, if it's an AC signal, is flowing into and out of the wire periodically, but the current further down the wire, further along the wire, let's bring this top picture up. So let's imagine that this place we're looking at here on the left, where I've labeled plus V, that's the end of the wire. The current is flowing in and out of the wire at some frequency, and further along the wire, the current is not flowing at the same along the wire to the right at the same time as it's flowing to the right at this front end of the wire, at the entrance to the wire. So as a function of distance along the wire, the current at any given moment is sometimes pointing forwards and sometimes pointing backwards. Okay, sometimes pointing downstream and sometimes pointing upstream. So we should remember that the current is not pointing always in the same direction all the way along the wire in a sufficiently long AC cable. Okay, so here we are at some particular Z value on the right when the voltage has become negative. And now the electric field is pointing inwards and the current is flowing out of the page. And now everything is reversed. Of course, the magnetic field is now pointing anti-clockwise. But if we take the cross product of the electric and the magnetic field, the Poynting vector is still pointing into the page. So in the AC signal, there is no net constant current flowing along the wire, but the power still points in the same direction at all times. Okay, so the AC situation is a combination of the left-hand picture and the right-hand picture, and our conclusion is the power still flows into the page, okay, in the same direction regardless of the phase. All right. Now, the next part of question 1 was the following. It says, show that for a DC voltage V, so we're thinking of the DC situation again, and a resultant current flow I, that in a coaxial cable, if I integrate the Poynting vector over the dielectric area, that I obtain V times I. So part of this was covered in example sheet 4 that I've already posted the answers to. And again, we think of our situation, our DC situation, where I can calculate for a given voltage, which is due to a charge per unit length along the wire. So this is for the central conductor. Okay, around the wire, the electric field has the form Q tilde, where Q tilde is the charge per unit length, divided by 2 pi epsilon r epsilon naught r. So that's the electric field. And that electric field, as we showed in the example sheet, can be related to the voltage. And we can see that the electric field falls as 1 over r. And then there is a factor which is due to the sizes of the core and the sheath. Okay, so the core has a radius A. That's the outer radius of the core conductor. The conducting sheath lies at a radius B, and the dielectric lies at all other distances between A and B. So that's the electric field. So that's a little harder to work out than the magnetic field. The magnetic field is much simpler. The magnetic field is simply mu naught I over 2 pi r, which of course we know very well. So our job again is to integrate the Poynting vector. So our Poynting vector, so remember that formally speaking, the Poynting vector S is 1 over mu naught E cross B. And what I'm calculating here is I'm calculating the instantaneous value of the Poynting vector. So so I'm trying to calculate the instantaneous value of the Poynting vector, and here I'm calculating its IV at any particular moment over 2 pi r squared, and I simply multiply E and B together because they're at right angles, and of course everything it cancels out apart from the log B over A. So at that particular instant, I integrate the Poynting vector over the area of the dielectric, which of course lies between radius A and radius B. And to do that integral, I divide it into an integral over d theta. That's the polar angle from 0 to 2 pi. And I integrate over the radius, which of course is where the 2 pi r squared comes in. And then I have this constant factor IV divided by log B over A. Now remember that I and V, this is in a DC situation, these have constant values. But of course, I'm also thinking about here the AC situation where I and V may vary with time. So we can do both calculations together. Well, oh, I'm sorry. Yes, you're right. Absolutely right. I have missed out on a factor R, haven't I? When I should have written RDR here. So that's in the answers to example sheet 4. There should be an RDR that I've forgotten to write here. So the contribution at each particular value of R to the integral should be RDR. So they should add an R in there, and I'll add that to the answers. Okay, so when I do 1 over R dr, that becomes log of R, and log of R between A and B is log B over A. So that's how I go from this part of the expression to this part. Okay, so let's go through that in stages. So the integral over angles is 2 pi, and that cancels with the 2 pi over here, okay, which is inside the integral with dr. So 2 pi over 2 pi goes away. And the integral of r over r squared dr is log of r, and log of r between A and B with my limits is log B over A. So that's this part here. And log B over A divided by log B over A, of course, is just 1. So the only thing I'm left with is IV. So yeah, I just forgot that R value there. Okay, so there we are. So that tells me the instantaneous value of the Poynting vector is equal to I times V. Now, the integral of the Poynting vector is equal to IV. Now the integral of the Poynting vector, of course, is just the power. So the power that flows in the dielectric is the integral of the Poynting vector over that dielectric area, and that's just equal to I times V. So this is the solution for a DC current. For a constant I and a constant V, this is the power that flows. But I can modify this statement in the case of an AC situation where I have a peak current I and a peak current V that are both varying sinusoidally. And if they're varying sinusoidally, then when I take the average, it's a square root of 2 for each one of those. So therefore, the average power is just I naught V naught over 2. So that's another way to look at the answers in example sheet 4. Okay, so example sheet 4 has this question phrased in a slightly different way, but it's worth looking at it twice. So yeah, again, I'll just put that R into the answers later. Okay, so that's how to relate the Poynting vector to the I and V values in either a DC or an AC coaxial cable. And the interesting thing here is that the power is being carried within the dielectric. Okay, so just to summarize, the power that's flowing, our Poynting vector, exists in the dielectric material between the conductor and the sheath. So when I carry power from one end to the other of a coaxial cable, it is being carried in the insulating layer between the conductors. And we can imagine, in a more general sense, if I had just two wires, say like what are commonly called a twisted pair, so like many mains cables, the sheath, the current flowing in the opposite direction, may not lie concentrically around this conductor. It may lie all to one side, in which case there would be an electric field that passes from one to the other conductor. Okay, just imagine two wires spread apart from each other. The power is flowing in due to the electric and magnetic fields which lie between the wires, not in the wires themselves. All right, so that's question one. Now let's look at question two, which is a graphical question which illustrates this idea a bit more. Now, I wanted you to look up what a strip line is. Now, in our derivation of the strip line equations, which of course is a modification to the transmission line, we talked about microstrips, because a microstrip is the situation of a finite width but thin layer of conducting material lying above a large width ground plane. So that's our idea of the printed circuit board. The traditional strip line has two ground planes. So in our traditional strip line, the way in which the strip line is made is by basically taking a coaxial cable and then flattening by banging on it so it's all flattened out. So I still have this conductor in the center, and as a first approximation, the sheath has been flattened out, so it forms two layers which are flat above and below the central core. So this is what's meant by a traditional strip line. So you can see here that approximately we can consider the ground layers to be large flat surfaces which lie some distance, equidistant from our central conductor. And in this question, question two, I said, let's imagine that the central conductor is thin. Now, of course, how do we draw the electric field in such a situation? Well, you did this in E&M last year. We can deduce what the electric field line shape is by using the method of image charges. So we imagine there's two image charges, one above and one below, which give the same effect as any charges which are created in these conducting layers. So of course, remember, the image charges aren't really there. The charges are actually really in these conducting layers, but it allows us to draw the electric field lines as they pass to the conducting layers. And we remember once more that the electric field must be perpendicular to the surface of a conductor. Okay, because the electric field would, in the parallel direction at this boundary must be zero. So because of that, my electric field lines can be drawn schematically as shown here. Those are the black lines. And then I imagine, well, what does the magnetic field look like? Now we can solve for the electric field, and we could in principle solve for the magnetic field, but I said here in this question, deduce and sketch the shape of the magnetic field. And the important thing to observe here is that we know that in any of these situations, remember this is a dielectric that lies between these two conducting layers, we know that the magnetic field must be perpendicular to the electric field. Okay, so because the magnetic field is perpendicular to the electric field, we know that at any point where the magnetic field crosses these electric field lines, it must be perpendicular to them, and therefore I can draw that electric field shape, sorry, that magnetic field shape. So you can see I haven't drawn it very well, but the point is that I can draw the magnetic field. And this is a useful technique in many areas of electromagnetism where I can deduce the shape of one field or of a potential by knowing that it must be perpendicular to another field. Okay, so that's how I draw the answer to question two. The magnetic field is perpendicular to the electric field. So again, I can deduce that the power must only flow in the direction into the page, right? Because I know the pointing vector only flows into the page, I can deduce that the magnetic field must be perpendicular to the electric field at all locations. All right, so that's question two. Again, as usual, please ask any comments or questions in the chat. Okay, so that's transmission lines. Now, we are now going to talk about waveguides, but on our way to talking about waveguides, we're going to talk about cavities, because cavities are a way of approaching the waveguide equations. But you can see here that this situation of power flow going through a transmission line, so this is our strip line, and we've seen other ones, we can see the basic concept that a dielectric material that lies between some conductors is the place where the power is carried. And the difference we remember between a strip line or a transmission line in general and a waveguide is that in a transmission line there are two conducting layers, whereas in a waveguide there is only one conducting material. But there is still a dielectric, and the power flow in that dielectric medium is due to the fact that the electric and magnetic fields are always perpendicular to each other. So we'll get to that in a moment. But before we do that, let's look at the microwave oven. So here's our microwave oven. So what I've drawn is the rough dimensions of that microwave oven box, and I've labeled them in the way we conventionally label them, which is I label them in order of size. So I've labeled the smallest size to be A, that's 15 centimeters. So that will define my X direction. My B distance is the next one, my B size, that's 25 centimeters. And my D size is 30 centimeters. So by defining it in that way, I have implicitly defined the directions of my X, Y, and Z vectors that we conventionally use. Now you could define all of these in any order you like, but it's easier to remember it this way round. So here's my cavity. And we remember that we said that the longest wavelength, the lowest frequency of any standing wave which can form in a cavity like this is when the electric field points across the shortest side of the cavity. Okay, so this is a cuboidal cavity. And the other part we said is that in order to have a standing wave formed, we had that there are three mode numbers. And remember, the mode numbers is the number of half oscillations which are, or half sine waves, which are made across each of the three directions. So you can see the labeling here, 0, 1, 1. Let's look at the D direction first. That's the last one. That says there's a half sine wave along the D direction. That's the third number here. The second number, that's the half, that says that mode number is 1, which says there's a half sine wave along the B direction. And the final number is 0, and that says there's no half sine wave at all in the A direction. So remember, there was a rule that to have a finite size for the electric field somewhere in the cavity, two of those numbers had to be not equal to 0. Okay, so 0, 1, 1 or 1, 0, 1 or 1, 1, 0 are the lowest modes for electric fields pointing in either the X, the Y, or the Z directions. And each of those will have different frequencies if A, B, and D are different sizes. But you can't have a mode like 0, 0, 1 or 0, 0, 0. You can't do those because there's no electric field at all. Now, what does this look like in terms of the boundary conditions? Does it satisfy our boundary conditions? Well, let's look at our 0, 1, 1 mode. Our 0, 1, 1 mode has a half sine wave in the Z direction. Okay, that's the 1 at the end there. So if I draw the strength of the electric field as a function of Z from one surface of the cavity to the other, it goes up to a maximum in the middle and then comes down again. The same thing is true for the Y direction. That number 1 means the electric field goes up to a maximum in the middle of the cavity and then falls to 0 again. And remember which way we said the electric field is pointing in this particular mode. The electric field is pointing upwards everywhere. So that means it's pointing upwards at the surface, in this surface at D equals 0, and at the surface at at Z equals 0, and at the surface at Z equals D. Okay, but because it has fallen, because its strength has fallen to 0, it satisfies our boundary condition that the parallel component of the electric field is 0 at z equals 0, and it's also 0 at z equals d. And similarly, it's also true in the y direction, where we have y equals 0 here and y equals b here, and the electric field must also fall to 0 there. That's the parallel component. Now let's look at the electric field at the boundaries in x. At x equals 0, the electric field is finite in the middle of the cavity, and it points straight out of the cavity. And that's absolutely fine, because there's no boundary condition that sets the parallel component has to be equal to 0. Sorry, the perpendicular component. Only the parallel component has to be equal to 0. The perpendicular component can be finite, and that's what we have here. So the electric field can point quite happily across this gap, this distance a, from x equals 0 to x equals a. And we can remark that the reason the electric field is being formed is because of the creation of transient charges on the top surface and the lower surface, which appear and disappear as the electric field grows and shrinks. So that's how I draw that electric field. Now, that's how I draw it. What does the shape again look like? Well, remember we said for the lowest mode, the electric field in the y direction and the electric field in the z direction are equal to 0. And if you look at the notes, you can see that the electric field in the x direction has the form E0, that's the strength of the field, sine kyy, sine kzz, and then it has this time varying part. Now, in the case of the 0, 1, 1 mode, right, well, you can see that there's no mode 0, so that there's no cos kxx in this equation, it's just 1. But in the y direction, there's a variation sine pi y over b, okay, because for ny equals 1, ky equals pi over b, and for the z direction, I have the same kind of behavior, kz equals pi over d. So you can see explicitly that the electric field becomes a maximum at b over 2 and a maximum at d over 2. All right, so let's plot that out. Let's see what that looks like. So here it is. So here is a static cavity. So this is what I mean by a static cavity situation. I'm plotting the electric field at a given moment in time. So I'm saying t equals 0 in this calculation. So I set some value for the electric field. This is just so that all the electric field arrows that I'm going to plot in a moment have the right size. And again, you can plot this kind of stuff out yourself using Python, Mathematica, or anything else that you like. And here I set, these are the dimensions of the cavity wall sides. Okay, so you see down here, I've got A, B, and D. And I set as an approximation that the speed of light is 3 times 10 to the 8. And all this will do is it will change slightly the resonant frequency when I calculate that. And I set nx equals 0, ny equals 1, and nz equals 1. This is our 0, 1, 1 mode. And again, if you look at the notes, you can see that I can define that the resonant frequency of the cavity in this mode is given by nx squared over a squared plus ny squared over b squared, and so on, with a square root. And then, of course, I have to change that wavelength into a frequency. Now, so this will tell me what that frequency is. So that frequency is 781 megahertz. So that is the lowest mode frequency. Now, what do the electric fields look like? You can see here that I define in general terms the electric field in the x, in the y, and in the z directions. And you can see that these all look the same. The thing I have to be careful about is that it has a cos form in whatever direction I am plotting. So if it's ex, it's cos kxx. If it's ey, it's cos kyy, and so on. And otherwise, it's sine. So that's exactly the same as it is in the notes. And of course, if I plot it out, let me just do the preamble material. We'll come back to this in a second. Just get rid of that. And if I calculate the electric field. Should come up in a second. There it is. Okay, and now I can rotate it. If it lets me rotate, there we go. Okay, so the blue lines indicate a low strength of the electric field, and the red arrows indicate a large strength of the electric field, and of course the direction the arrows are pointing is of course the direction of the electric field. So I can visualize the electric field, and as we can see, we see that the electric field points into the surfaces at x equals 0 and x equals a. That's the bottom and the top of this cavity. But the electric field is pointing along all the other surfaces at the surface, but the electric field strength falls to 0 at all the other surfaces. So that's what the lowest mode looks like. And of course, as a function of time, this simply goes up and down as cos omega t. So here I've set t equals 0 just to show what it is, but let's how are we going to do that? Let's do cos pi. Okay. I think I want to do omega t. What's the period now? I need to do t. Yeah, so I need to do. I think I want to do omega t over 2, right? So I'm plotting half a period different, aren't I? Let's try that live, see if that works. So hopefully I'm doing 1/2 period later. And as you can see, the electric field now points downwards. So if I do, let's see what it looks like at 90 degrees, 1/4 of a cycle. And it should be, let's see, no, okay, so that's not going to show very well because it's scaling all the arrow sizes. So it's very, very small, but it's still larger in the middle. So if I do I do t over 3, it should have inverted. So okay, I'm doing this live, obviously. Okay. So you can see that there's an automatic scaling being done on the arrow colors. But of course, if I move slightly later in time, I've gone past that 0 point where the electric field falls to 0 through the entire cavity. And now the electric field is now pointing the other way. No, it's still pointing up there, isn't it? I'll need to, yeah. Why is it still pointing up? It definitely points down after half a period, doesn't it? Let's have a look. Half a period is definitely pointing down. Okay. Okay, well, it'll be easier when we plot the higher modes, which I'll do in a minute. But anyway, the basic idea still remains that the electric field is pointing into the surfaces on the boundaries of X. Right, so that's how we do it. So that's our lowest mode. So just formally to write it down. So if we look back at the notes, the minimum frequency in the lowest mode, remember there's no mode number in A, that A equals 0. Okay, so nx equals 0. So there's no mode number in A. It's just 1/b² plus 1/d². And if I convert that to frequency, okay, then I divide by 2 pi and I pop those numbers in, it's about 780 megahertz. Now, this is where it gets a little trickier. Let's look now at question 4. So for the microwave oven cavity in question 3, calculate the frequencies of the first 5 modes. How do these frequencies compare to the commonly used magnetron frequency of 2.53 gigahertz used to power microwave ovens? Well, let's look at that. So you can see here that these dimensions, 30 centimeters by 25 by 15, is something like the size of a microwave oven cavity. Okay, so I've made D and B different to each other so we can see 2 different values appearing. So most often in a microwave oven, 2 of these dimensions will be the same, just for manufacturing simplicity. But these aren't far off being the kind of frequencies we'd imagine. So you can see straight away that the lowest mode frequency is 781 megahertz. So if I had a power source of 781 megahertz and I fed it into this microwave oven, then the electric field in the center would be strong and the electric field in the boundaries of the cavity would be quite weak. So I would only cook food in the center of the cavity. That's where the power is concentrated. So if I had a thin cup of coffee extending between the bottom and top of the cavity, then it would cook reasonably uniformly all the way through. But if I put it in one of the corners, it wouldn't cook very well at all. Now, in reality, we use a magnetron of a higher frequency. So if I fed microwave power at this frequency only, it would couple into this mode. But if I fed it at a slightly different frequency, then there would be some sort of mismatch, and I wouldn't effectively couple power into this particular mode. Now let's go back, and we'll go back to these equations up here. So I'll put these on. I think these are already on Blackboard. So let's put in our equations for the cavity mode frequencies. So I put c as the speed of light, and I calculate explicitly using the notes the frequency omega as a function of L, M, and N. This is Nx, Ny, and Nz, and A, B, and D. And I calculate their frequencies by doing that divided by 2 pi. And you can see I can explicitly calculate the frequencies of each mode. So these are the mode numbers here, 0, 1, 1, and these are the dimensions of the cavity. And you can see here, this one is 781 megahertz. Let's try making a very, very flat microwave oven. So this is a microwave oven that is very, very wide, has the same depth, but is now only 1 centimeter tall. As you can see, it has an identical frequency. And that's a consequence of the electric field pointing from bottom to top in the cavity. So let's just plot that. If I plot that below, you can see here that I'm going to make the dimension A 1 centimeter, and I plot everything again, and I should make that equal to 0 for 0 time, so we can see. So this is 0 time, and you can see this is a very flat cavity. Okay, so the electric field again points from the bottom surface to the top surface, but it does point across, and the resonant frequency has not changed at all. That's an important thing to notice. So let's go back up again, and we'll go back to the question number. So that was 15 centimeters. So the lowest frequency is 781 megahertz. The next frequency is 101, or the next mode I can label is 101. Remember that one of them can be 0, but the others have to be 1. So that's 1.1 gigahertz. And the next one after that is 1.66 gigahertz. But now I start to wonder, if I look at all the different modes, which ones come first? So that's a bit fiddly. Let's calculate them. So you can see how I'm going to calculate my mode frequencies, and I'm just making a table of them. So I'm scanning over all the values L, I'm scanning over the values M, and I'm scanning over the values N. And I'm only writing numbers out to this table if L plus M plus N is greater than 1. That's my condition on having a real mode in this cavity. Okay, so the frequency. So what I've done here is I've sorted. Let's calculate this. Now what I'm going to do is I'm going to get rid of this flattened bit here, and I'm just going to write out what the frequencies are. So I'll just turn them into numbers. Flatten. So these are all the frequencies of those modes where I've just gone, N goes from 0 to 5 for L is 0 and M is 0. And then I step upwards 1 in M, and then I do it all again. So these are not in any order whatsoever. So it's kind of hard to see, isn't it, which ones have the lowest numbers. So that's why I'm sorting them. So I put a numerical sort, and now I can see what they are. Now, the way you can do this manually is to manually calculate, let's say 0, 1, 1, 1, 0, 1, 1, 1, 0, and then you might go 2, 1, 0, okay, 1, 2, 0, 0, 1, 2, 0, 2, 1, and so on. You can manually calculate them and then figure out which frequency is which. So that's time consuming, you can do it. What I've done here is I've just written a formula and then sorted out the frequencies. And what can we see? We can see here that the first frequency is, of course, our lowest mode. That must be the 0, 1, 1 mode. The next one is at 1 gigahertz. The next one is at 1.12 gigahertz. And notice here, the next two, this is why I chose these particular dimensions, the next two are both at 1.67 gigahertz. So if I happen to have a power source which was feeding power in at 1.16 gigahertz, it would excite both of those modes. So I'd have an electric field at in two of the modes, but I wouldn't be exciting in any of the other modes. Okay, and so that's 1, 2, 3, 4, 5. So you could consider these two frequencies are the same. So you could say that's your top frequency, Or you could also say that this one at 1.2 gigahertz, that's the 5th frequency. So those are the 5 distinct frequencies. So it's a bit fiddly to figure out which one's which, but you can do it, okay? And you just have to attach the mode numbers to those frequencies as you write them out. But I'll leave that for you. That's less interesting, isn't it? So those are the lowest 5 frequencies. So you can see, let's look at the big list of frequencies. You can see there's loads and loads and loads of modes up to 2.5 gigahertz. How many are there? 1, 2, it's about 10, 20. There's about 25 or so modes up to 2.5 gigahertz. Now, remember what we said about when we have devices which are oscillating and where we're trying to transfer power from one to the other. So this applies for transmission lines, it applies for cavities, it applies for many things. We know that there will be an impedance between the thing that's delivering the power and the thing that's receiving the power. So you can see here, our cavity here will receive power. It will have a minimum impedance when the power that's fed into it matches one of these mode frequencies. However, we also know that these kind of things have Q values. Okay, so this is an oscillator. So like any oscillator, an oscillator has a Q value, and we'll look at the Q value in a later lecture. The oscillator has a Q value, and that Q value will be finite, and therefore we can excite these frequencies even if we don't precisely feed power in at those frequencies. So the consequence of that is, if I have some frequency, say 2.5 gigahertz, it can excite a lot of these modes. So if I feed power in at 2.5 gigahertz, it can excite a lot of these modes, and I will get what is called a multi-mode electric field. I will have a number of different frequencies all oscillating together. And this is why in a microwave oven, I can consider that the electric field is more or less uniform within the cavity. So that's why that arises. So just to finish off, let's look at those higher modes. Let's see what they look like, because we're going to move on later to look at waveguide modes. So here is another mode, and this one is more interesting because this demonstrates the difference between the 011 mode and the 111 mode. So remember before we said that in the 011 mode, the electric field was constant in strength from x equals 0 at the bottom to x equals a at the top. So it pointed in the same direction all the way through. Here, this is different. In this 111 mode, the electric field, as you can see, points up at the bottom and it points down at the top. And you can see there's a couple of other things. The electric field also points inwards on all the other sides. So this is a different mode. This is the 111 mode, and you can see that I still satisfy all the boundary conditions. The parallel component of the electric field falls to 0 at every single surface on this cavity. So that's the 111 mode, and you can play around with this. You can change the mode numbers to larger values if you like, and you should be able to get more interesting. Here we are. So you can see here, this is a higher mode. This is the 321 mode, and you can see it has another pattern. You can see the places through the cavity where the electric field is changing signs, and it changes signs a certain number of half wavelengths in each of the 3 directions. So that's how those mode numbers translate to being the orientation of the electric field. And you can see there's a symmetry here because this is a cuboidal cavity. Okay, so that's the cuboidal cavity. Now the final question was the cylindrical metal biscuit tin. And the job here was to simply draw what the electric field looks like. So the electric field in a cylindrical cavity, and you can by now guess that if the cavity is wide and short, in other words, of large diameter, here 30 centimeters, and short 5 centimeters tall, then the lowest mode will have an electric field which points across the shortest side. Now, we know from our previous considerations, which you've done in massive ways in fields and in other situations, that we know that the shape of the electric field must have some Bessel function form. So we're not going to do the detail of that here, but we do know that the basic idea is that the electric field strength, again, must fall to 0 on this surface here. This is the curved surface of this biscuit tin. And so because the electric field falls to 0 there, and it has a maximum in the center, we can write down what the electric field is as a function of radius, and it will have this form in all azimuthal directions at all angles theta, where theta varies from 0 to 2 pi. Now, what is the wavelength of that? Well, we know straight away that because this Bessel function looks something like a half sine wave, then roughly speaking, the wavelength which can be supported by this cavity is something like 60 centimeters. Now, we know it's not exactly 60 centimeters, and there's a couple of ways you can write it out, but formally, the lowest mode frequency is given by 2.405 divided by r, where r is the radius of the cavity. That's 15 centimeters in this case. And that 2.405 number comes from the solution of that constraint on the Bessel function, that it must fall to be 0. This is the first. This is the Bessel function. This is the first order Bessel function. Okay, it falls to 0 at r equals 15. Okay, and that value gives us a frequency of 2.405 c over r divided by 2 pi, and this turns out to be 766 megahertz. So you can see that because this cavity has a rough size of 30 centimeters, which is not far away from the 30 and 25 we had before in our cuboidal cavity, that the resonant frequencies are much the same as they were in the cuboidal cavity. Okay, so you can write that frequency in terms of wavelength. It's basically the radius divided by 0.383. Okay. So you can, again, just to finish, that the height of this biscuit tin, the height of this cavity, has no relation whatsoever to the resonant frequency of the cavity. So just to illustrate that, I may have shown this on one of the videos. Hopefully you can see me. Let's just pin myself so you can see me. Okay, so here is one of those cavities. So this is a life-size 3D print of a multi-cell cavity. So each one of those resonant biscuit tins is one of these little apertures. Okay, and you can see here that there is some kind of hole going in and out at one end of each of those cells. But the commonality is that the diameter of these circular apertures, the diameter of that, are the same for all of them. So therefore, they all have the same resonant frequency. And because they all have the same resonant frequency, that means that they can pass small amounts of electrical field from one to the other through these apertures. So they will all be coupled together. These are coupled oscillators, and they all resonate together. So they all resonate together at the same frequency, and they all have an electric field which points in some particular direction. We can arrange which way they point, such that when particles pass through from one end to the other, they can be accelerated by that electric field. So this is a device that accelerates particles along a straight line, and is why we call it a linear accelerator. Right, so that's the end of today. Now, I realize that I haven't gone through question 5, which is the waveguide question. Hopefully you already had a go at it. We will go through that question and a few others next week. I think we've more or less run out of time for today. So hopefully you found that useful and a useful adjunct to what we did in the teaching videos. And as per usual, please post any questions on Piazza, and hopefully we'll see you next Monday. Okay, cheers all. See you later.